over, say, sigma to the n, such that restricting to any k coordinates, what I'm seeing marginally is the uniform distribution. We constructed such distributions for k equals 2. Let's do it for general k right now because it's also simple. Okay. And we'll construct them over a finite field, say of size n, but it's very easy to transform into binary, just any sensible way you can think of. So I need to tell you how to index a sample space. So here, what I do is each row I index by k coefficients from my field, say a0, a1, up to ak minus 1. And what I output for the ith variable is just the evaluation of this low-degree polynomial that is given to me by the coefficients aj on I. And I view everything as a finite field element. Okay, so how do I sample from a distribution? I just pick a random row and just output this row. Okay, so is the definition of the distribution clear? Okay, so one thing to note, remember that I told you we love distributions with small support size. So the uniform distribution has n to the n size. And this distribution has support size only n to the k. Right? Good. This space will be sufficient to prove that it's indeed a k-wise independent distribution. What do we need to show? For any fixed tuple alpha, I want to show that the probability to see alpha is n to the minus k. Let's just do it for k equals 3, and then you'll all be convinced. So the probability is over A, and I want to show, say I'm given I1, I2, and I3. Okay, let's do it for k equals 3. So I want to see what's the probability that A0 plus A1, I1 plus plus A2 I1 squared is equal to alpha 1, A0 plus A1 I2 plus A2 I2 squared is equal to alpha 2, A1 I3 plus A2 I3 squared is equal to alpha 3. And what is it? I can just write it as 1, 1, 1, I1 squared, I2 squared, I3 squared, A0, A1, A2. Now the indices are fixed, alpha is fixed, the probability is over A. Okay, so this is called the Vandermonde matrix, which is here. We know it is non-singular, so we can just multiply by the inverse and get just, what's the probability that A is any fixed k tuple? It's just n to the minus k. Okay, so a very simple construction of a k-wise independent distribution. Let's see.
There's another way to do it, right? Like if you think it is a polynomial.
Right. As a low degree polynomial, any k minus 1 points on it are distributed uniformly. That's another way to see it. Right. Thank you. Okay, let's see now two applications of k-wise independent distributions. The first one would be the nice notion that we like in pseudorandomness, which we call like fooling the proof. So let's see. Let's prove, remember we talked about it yesterday, there exist bipartite graphs, n by n bipartite graphs with no k by k clicks for k which is 2 log n. Let's prove it. Easy. We draw a bipartite graph at random. Each edge is an edge. Each pair is an edge with probability half. And now for given subsets of size k, what's the probability that the induced subgraph is complete or the induced subgraph is empty? It's exactly 2 to the minus k squared. Okay, do you see it? And now union bounding, or asking like what's the expected number of cliques plus the expected number of independent sets. If you do the math, so okay, this is the probability that it's complete or empty, and this is just the number of pairs of subsets. And if you plug in k, which is 2 log n, you'll see that it's strictly less than 1. So there exists such a graph. Okay? Simple. But we want to find one, and okay, the proof tells us that there is one, so let's brute force. But brute forcing takes time, which is exponential in the number of vertices of the graph. Okay, so this is the dominant factor. But did we really need to choose the edges using full independence? So if you look at the proof, sorry. Good. So if you look at the proof, this equality holds even if the edges are chosen k squared wise independently. Okay? And that's the only place we used randomness in the proof. So how about not choosing them at random? Let's choose them with bounded independence. So let's take k squared wise independence generator that gives us the edges indicator, so it's n squared. Okay, so remember that the seed length is like k squared, the wise independence, times log of n squared, which is 2 log n. This is t. And same proof works. So now, instead of enumerating over all graphs, we can just enumerate over the image of G, of the pair G for the chaos independent generator, right? And now the runtime is dominated, well, this one is roughly the same, but 2 to the t, which is big N to the O of k squared. Okay? So it's quasi-polynomial in the number of vertices. Of course, people in pseudorandomness kind of might feel uneased because usually even poly-n is not enough for us because we like to view a graph as the adjacency function. So ideally, what we want is to run in polylog n time and decide whether there exists an edge between two vertices. Okay, so this gives us quasi-poly time in the number of vertices, not in the length of the input. Okay, but it's kind of a nice application of k-wise independence. Questions? Let's see a second application, which I'm not going to show. But remember the list that I showed you, what is full by k-wise independent distribution, all the lists contained like easy, I mean, you could see k there, so it's not very surprising. But like the beautiful work of Braverman actually proved that k-wise independence full low depth circuit. So let's recall what a circuit is. So that's a Boolean circuit, right? It computes a function over n variables using ORs, ANDs, and NOT gates. The size of a circuit is, say, the number of the wires here. And the depth of a circuit is the length of the longest path from the output to a leaf, to an input, to a variable. Okay, so usually, so we say an AC0 circuit, we usually mean that the depth is constant, and it has some size S. And Braverman showed that k-wise independence, specifically this K, fools AC0 circuits. So for any such circuit, the expectation of C of D, where D is a chaos independent distribution, is approximately the expectation of C on the uniform distribution. So see, there is no K in this model, so it's a kind of a deep result. So what goes right? Okay. So before continuing, note that it gives a PRG of this seed length, right? Take this K times log of the size. Well, log n, but say log s. Say n is s. Okay. So just to what goes into the proof? Of course, we're not going to prove it, but what is being used? Chaos independence fools degree K polynomials. This we said. The notion of average case computation of AC0 circuits. You have an exercise along this line due to Smolensky. The LMN result of L2 approximation of AC0 circuits. This uses Fourier analysis and random restrictions, both of which we'll hopefully talk about. Subsequent works improved the K that is needed to fool AC0 circuits. And for those of you who are kind of sharp enough, I told you that this gives a generator for AC0 circuit, but those do not give the best generators for AC0 circuits. And I will talk briefly about what is the state of the art, hopefully on Wednesday. Thursday. Okay, questions? Good. Moving on. Small bias distributions. Okay. What is that object? What we're after is a sequence of random variables, say over 0, 1, but it can be over any, say, abelian group even. We say this sequence is epsilon bias if for all non-empty sets S sub S, it holds that the parity of the xi's, where I is in S, is balanced up to some epsilon. Okay, over F2, you can switch the parity to a sum. Okay, so let's imagine we're working over F2. So in terms of PRG, what it says is that X is epsilon biased if it epsilon fools, which what's curly F now? Remember, what's curly F? Linear functions over F2. Okay, that's our function class. Okay, so we want a generator G with a short seed such that its image, or the uniform distribution over its image, is epsilon biased. Questions about that definition? Good. Let's kind of play around with this. Let's kind of play around. So we can remember that we can. We don't even need to, but let's switch the parity with the sum, and saying that the parity is almost balanced. It's saying that the expectation of -1 to this sum of xi, where I is in S, has small expectation. Right? You see, it's roughly the same. It's the same up to 2 factor. Okay, those two are the same. Now, what is this function? -1 to sum of xi, I is in S. This is what we call chi-S, the additive character of the group Zn to the Z2 to the n. Okay. So, alternatively, we say that X fools all non-trivial additive characters of F2 or F2 to the n or Z2 to the n. Okay. Make sense? And this is kind of a way for me to introduce the Fourier coefficients, because the additive characters form an orthonormal basis for the vector space of functions from F2 to the n to C. So it means that I can write any function, f, as a sum of f hat s, it's just a coefficient, the Fourier coefficient of the function, times chi s of x. Okay, that's called the Fourier decomposition of a function. Okay, so let's see how, so you can see how those two relate. So which classes do small bias distributions fool? So of course, degree 1 polynomials over F2, but also functions with small Fourier L1 norm. What do I mean by that? So take any function. Let's write it in its Fourier form. What's the expectation of f of x minus the expectation of f on the uniform distribution? Now, the expectation of f over the uniform distribution is just the coefficient of the empty set. Do you see why? Because, right, so what's f hat of the empty set? It's just the normalized inner product between f and chi of the empty set, which is just the all ones function. Okay, so this is the expectation of f under the uniform distribution. And what's the expectation of f of x? Let's take the expectation here, okay, and use linearity of expectation. Take triangle inequality. Then, okay, it should be here 2 epsilon. But if x is epsilon biased, the expectation we saw previously is bounded by 2 epsilon. So we get this L1 norm. So if this L1 Fourier norm is small, then x fools f. Okay.
I guess you say what happens for the empty coefficient. X.
Right. Sorry, so what's... but it's 1, so it cancels. Right. Yes. Okay, so which functions have small Fourier L1 norm? For example, if you know branching programs, so with two read once branching programs, bounded side decision trees. I will mention a very nice work that characterizes such functions. So they have some affine structure. And if you kind of think, well, maybe, class of degree 1 polynomials over F2 feels kind of limited. So I'll just tell you that it's used as a building block in many PRGs for more powerful class of functions. We'll see one example now, but there are really many examples. Questions?
What was our assumption here exactly? It's epsilon biased?
Yeah, so that the expectation of chi s of x is get most to epsilon because x is epsilon biased.
And this is true for all subsets S?
Non-empty. Yeah. Good. Okay. Now let's see the connection between small bias distributions and error correcting codes. So I'm not going to go deep into error correcting codes. I just want you to to know one thing and kind of one central challenge in error correcting codes. So in error correcting codes, what we want, one of the things we want is just a subspace of, here I denote F2 to the n bar. That I want it to be very large on the one hand, but on the other hand, I want its points to be far away from each other. Okay, so I want a linear subspace, and I'm explicitly writing it as an encoding function. So it has 2 to the n elements. It has dimension n. Okay, and the ambient space is f2 to the n bar. And I wanted the Hamming weight of each code word, of each element in the vector space, to be at least almost half, so half minus epsilon times n bar. And it's a simple exercise to show that since C is linear, it is the same thing as requiring that the distance between 2 points is at least d. So think about it. We want to construct explicitly subspaces that have many points, so with large dimension, but where every 2 points are almost as far away as possible from each other. So we want to maximize the rate, which is n over n bar, as a function of n and epsilon. Now I want to show you that it's basically almost the same thing as epsilon bias. Let's take an epsilon bias set S, which is a subset of f2 to the n. Say it has elements s1 up to sn bar. Just rotate it. Okay, just rotate it. You'll get a matrix. This matrix will generate the subspace that we want, because just treat x as a test vector. Okay? Any non-zero x, treat it as a linear test. The epsilon bias guarantee will tell you that up to epsilon, it's exactly balanced. So this will be your subspace. Okay, and it's a very important question. This kind of challenge is extremely important in coding theory. Okay. Okay. Here's another connection, this time to Cayley-graphs. Okay, we've heard quite a bit about Cayley-graphs. Let's see their connection to epsilon bias sets. So let's take a Cayley-graph where the group is Z2 to the n, and the set of generators is an epsilon bias set. So we have a set of generators. We have, and just take the Cayley graph over this set of generators. So for any vertex u, I just take the set of elements in the epsilon bias set and just connect, for example, u to u plus s1, u to u plus s2, u plus, to u plus s3, etc. Okay, so that's the Cayley graph that you get. And what we want to always argue is about the expansion of the Cayley graphs. And here it's easy, because for any S, the eigenvectors of G are the group's characters. Let's see why. So take any function over the vertices or any vector. This is how the normalized adjacency matrix of a Cayley graph over an abelian group behaves, right? Now let's just take f to be chi a, any character. This is just plug and play. So this is -1 to the inner product between a and u plus s. And now we can pull chi a u outside the sum. So and this stays. So what we get is chi a of u, which is exactly the same thing we have here, times the expectation of chi a over my epsilon bias set. So the trivial, we should expect some, trivial eigenvector and eigenvalue because it's a graph. So here we have chi of the empty set. And for any other a's, the epsilon bias guarantee tells us that it's at most 2 epsilon. Right? Okay, so we got for free a 2 epsilon spectral expander. Okay. Questions? Jumping a bit ahead, maybe some of you already know that we cannot hope to get a constant degree Cayley graph from such a construction, but those constructions have other very favorable properties that we use. Okay, so it's a very important question. A lot of work was dedicated to it. So what's the smallest n bar we can hope for, again, in terms of n and epsilon? So non-explicit, it's n over epsilon squared. That's the probabilistic method. And it almost matches the upper bound that we have. Lower bound, sorry, it's like rate is upper bound, size lower bound. It's almost tight. I will show you very soon the simple, what we call the AGHP construction, which gets n squared over epsilon squared. Now, because of the construction decoding theory, we really care that here it's n and not something else, because that means the rate only depends on epsilon. About 10 years, and so you can see kind of the progress. About 10 years ago, there has been a huge breakthrough by Amnon Tashma, who got nearly the correct expression. I will talk about it very briefly when we get to expanders. There's been some follow-up work suggesting alternative constructions. I kind of split those constructions like this, because I just want to mention that there are basically two main techniques for constructing those objects. One is via what we call code concatenation, if you know about it. And the other is via what we call distance amplification. I will talk about distance amplification very briefly, hopefully, in the next lecture.
What do you believe to be the right answer?
I mean, we have been trying to suppress that. So, yeah. I spent some time trying to show that it's not optimal. So I at least have some belief in that. Questions?
Are there any really interesting applications if you get rid of the little o one?
You know, the codes will be contain much more elements, because you like kind of need to it's like 2 to the n, so it's really any shaving of this little o of 1, and you know some of these works, that's what they deal with. This little o of 1 is meaningful for codes. Coding theory people don't view that as kind of an optimal code. It's not like it's not on the GV, it's not close to the GV bound for them. Okay. So I'll just mention that in terms of PRGs, we care about the seed length. So sure, in all those constructions, the seed length is like O of log n over epsilon, but in this particular problem, we care about the actual constants. Okay. Good. Here's the AGHP construction as a PRG. So let's set some Q to be, let's set it to be n over epsilon. And the seed will have two parts, y and z, two field elements. It's a uniform seed. And what we output is simply the inner product between y and z, yz squared, yz cubed, etc., up to yz to the n. We first view those as field elements, and then take, say, their representation as binary vectors, and take the inner product mod 2. Simple construction. Again, the correctness fits half a slide. So we want to show that it fools any linear test. So let's fix any linear test. F of the output of the generator is just we sum over all I and S of the inner product of y and z to the I. So let's use the linearity. This is like the inner product of p of z, where p is just a polynomial sum over I in S z to the I. Okay? So it's a degree n polynomial. And let's see what is the expectation. We want it to be close to half. So we have a y component and a z component. Now, if p of z is 0, we don't get anything, so the expectation is 0. And if not, so this happens, right, sorry. So, okay. If it's 0, then it's 0. If it's not, so if you get any non-zero thing here, and y is uniform, so what's the expectation? It's exactly half, right? So if here the second argument is fixed, and you ask what's the expectation of a uniform y of the inner product between y and something fixed, it's exactly half. So all that's left to do is to bound the probability that p of z is non-zero, and we use kind of the degree mantra, saying that because p has degree n, it has at most n roots, so the probability to hit any root is at most n over q. So that's why we choose q to be sufficiently larger than n. Okay. So already this simple construction gets us O log n over epsilon seed length for epsilon bias sample spaces.
You can also view it from the coding's perspective, and maybe
Right,
it's
so
more
if
natural
you
construction.
right. So if you if you know a little bit about error correcting codes, this corresponds, and you want to see how like the correspondence to coding to the code. This is just the Reed-Solomon code concatenated with the Hadamard code. Maybe there it's even easier to see the correctness. But yeah, just if you know what those codes are. Questions? Okay. One last application, I think, of epsilon bias sample spaces is for fooling small degree polynomials. So we want a generator that maps S bits into an n tuple of field elements such that for any degree D polynomial p over f in n variables, kind of the distribution of its output on the uniform distribution is close in total variation distance to the distribution of its output on the generated distribution. Okay, so here curly f is the set of low degree polynomials over a finite field. Okay. Here's what the probabilistic argument will give you. D log n over d plus log 1 over epsilon plus log q. And we already know how to handle the case of d equals 1. We know it over F2, but believe me, similar construction works over any field. Okay. What about when Q is very large? Never mind for now what's the very. But when Q is very large, it's large. It's large. We do have nearly optimal constructions. Okay, there's been quite a lot of work on this. It's a well-studied problem. And Q being large is usually the easier case because we have a lot of math when we have a large field. We have only 2 elements. It's more challenging. And it's actually provably more challenging because if you can get non-trivial PRGs when d is larger than log n, it would give new circuit lower bounds. This is really a barrier. But what's known about the Q equals 2 case? Let's see. So this is due to Viola. The idea is very natural, due to Bogdanov and Viola. Well, we know that for d equals 1, we have small bias generators. What about larger d's? Well, let's take some number of independent copies of, say, epsilon prime bias generator. Okay, so this is the construction. We have L of D independent seeds, and we just sum them together over F2. Okay. And Viola showed, so previously it was known that I think it was 2 to the D sufficient for I think, right? 2 to the D for some regime. But Viola was able to show that D copies suffices, but you need to take epsilon prime to be considerably smaller than the epsilon is the kind of final error that you want. So you need to take epsilon prime to be epsilon to the 2 to the D. And this gives us the seed length, which has this unfavorable 2 to the D here that, of course, we would want to get rid of. Okay, so I'm not going to go over the proof. I will just mention like what are the ingredients that go into this proof in case some of you are interested. So it's the proof by induction, and we actually need to approximate the bias, right? Because for F2, the bias is just it's similar to approximating the output distribution because just 0 and 1. And it has two cases. Either my polynomial is balanced or it's unbalanced. Turns out that not nearly balanced is the easier case because it turns out that if you have some distribution that fools degree D polynomials, it already fools degree D plus 1 polynomials up to this bias error. And it uses the notion of directional derivatives that kind of automatically reduces the degree by 1. This is how the induction works. This is the easier case. And the nearly balanced case, this is what you get. If W fools degree D and L is epsilon prime biased, then W plus L, which is our actual construction, fools the bias. Actually, this is 0, so you can say approximate 0 with this L. Very elegant and clever proof. One kind of takeaway that you can take is that if you have basically any functions, f and g, that maps to F2, any f and g, then you can approximate kind of the correlation between f and g, so the bias of f of u plus g of u prime for u and u prime uniform independent, using u and u plus L for L being an epsilon bias distribution. So it's kind of a nice takeaway.
Pointing out the connection to expand mixing.
Right. I chose not to mention, but you're right. There is also a connection to expand mixing. Questions? Okay, let me skip that for the sake of time because I will upload the slides, by the way. Sorry. Okay, good. Questions about epsilon bias? Let's move on to our next object, which is a sampler. A sampler comes to answer the following very natural question. So we have a function f. Say the domain is 0, 1 to the m. The codomain is just, say, 0 to 1. And we want to estimate the expectation of f of u using few queries to f. Deterministically, we cannot do much unless we assume some structure. That's why we have randomness. And kind of the obvious randomized algorithm would be to choose x1 up to x capital D uniformly and independently at random and return the average of the fxi's. Okay, and sure enough, Verhofting tells us that this D is what you should take if you want to epsilon approximate the expectation additively with probability at least 1 minus delta. Right? This is what you would do. And we want to kind of abstract this phenomenon. So You cannot do better than this D in terms of the number of queries. But the problem is, so the number of queries is good. I mean, we cannot hope to do better. But what's not good? The number of random coins needed to sample my inputs to the function. So remember that f is defined over 0, 1 to the m, and we choose d independent copies, so it costs us d times m random coins. So what we want is kind of a function that gets a short seed, hopefully, and tells us exactly which points we should take in our sample space. And this is called a sampler, specifically an averaging sampler. So we say a function gamma that gets a seed, 0, 1 to the n, and outputs d elements of 0, 1 to the m. We say it's a delta epsilon sampler if with 1 minus delta probability over my seeds here, I can epsilon approximate the expectation of the function. Okay. Is the definition clear? What, sorry? F here? It's f of the uniform distribution. What?
F of gamma of xi.
F.
Summation.
Oh, yeah. Sorry. Yes. F of gamma of xi. Yes. Thank you.
I can think without also generality of f as a Boolean, right?
True, but that's a claim, right? You can think of f as Boolean. Yes. Good. Okay, so just pictorially, we like to think of a sampler as a bipartite graph, where for any set on the right-hand side, there will be some bad elements on the left-hand side. Note that the bad elements depend on the set that you want to sample on the right-hand side. So for any set on the right-hand side, you have some bad elements on the left-hand side. But any good element sees roughly the correct fraction of elements in B or not. Here I am taking here I am taking my function f to be just the indicator of whether an element is in the set B or not. So I guarantee that for any good element on the left-hand side, it sees B roughly the fraction of times that it should see B. Okay, so this is my guarantee. Good. Is the definition okay? Okay. And we can do better than n, which is d times m. This is a trivial, remember this is a trivial sampler. So again, kind of the theme is, okay, let's draw a function at random, see how it behaves. Turns out that it behaves like this. So we can actually get n, little n, so the number of random coins is m plus. M plus, I mean, you need m plus. And the plus is very, very small. It's like O of log 1 over delta. Using the same big D that you get from Chernoff. Okay, so pretty impressive. And we actually have great express constructions nearly matching those parameters.
So no dependence on epsilon?
Right, log. Yeah. Thanks. But I chose not to show it. It's like it's kind of an unnatural setting that it really affects anything. Okay. And again, it's not only a nice object in itself, it's very useful. Not only in PRGs, but in many derandomization results. Okay. So let's take an example of two averaging samplers. The first one is using what we've just seen, which is KOS independence. So instead of drawing x1 up to xd independently, let's draw them from a KOS independent distribution, right? So we won't get this very nice end, but it will be something hopefully better than m times big D. And the question is, which k should we choose? I mean, the algorithm is clear. We saw how to generate a KOS independent distribution. So the answer is just which k should we which k should we choose? And this is where standard, maybe I don't know if standard, but tail bounds come into play. We can do a k moment argument to give a tail bound for KOS independent distributions. Okay, so one can show a concentration of measure phenomena for KOS independent distributions that behave like this. Okay, so you can, I'll give you a minute to digest. And if we choose this to be our delta, we kind of, you know, play around with parameters, this is what we would get. Okay, I'll give you just a minute to digest what's going on here. Okay, so what's good and what's bad? This is pretty good. I mean, we don't like this epsilon, but other than, I mean, it's pretty good. This isn't great, right? Because we want like log 1 over delta and not 1 over delta. This is for pairwise. You can do it for arbitrary k, but it doesn't really get that better. That much better. Okay. But it's better than the trivial sampler, so we're making progress, right? Simple construction, just using polynomials. Questions? Okay, let's see a second construction. Now, instead of drawing x1 up to xd independently or from KOS independent distribution, let's draw them according to a walk on an expander. So take an expander, a lambda spectral expander, over 2 to the m vertices. So each vertex here is the randomness string, right, that I need to sample, that I need to query. It's a string in 0, 1 to the m. And instead of like choosing x1 up to xd from, you know, the entire universe, I'm just choosing path on an expander. Okay. So what's the number of random bits? I'm choosing the start vertex uniformly at random, so it's m bits. And then I'm choosing, oh, sorry, it's not, it is, sorry. And then I'm choosing d times, so what I need to do, say I work with a very good expander, say with a Ramanujan expander. So what's the connection between lambda and the degree? Right, so the degree is like 1 over lambda. That's not, you know, it's not b. Yeah. So the number of bits I need to choose my next neighbor is log 1 over lambda. Right? Okay. Good. So this is the cost of sampling with expanded random walks. And now, what do I need to do to establish the sampling property? Which property of expanders? So we didn't see it in our expander talks, but it's called the expander Chernoff bound that tells us that we get essentially the same behavior as a Chernoff bound, as independent samples. All right, so we get the exact same Chernoff bound concentration, But we have this lambda here, and if we take lambda to be constant, and also the expander to be of constant degree, it's essentially harmless. Right. Okay. So if we play around with parameters, this is what we get.
I'm still confused.
Yeah, sure.
1 over lambda square root of the degree?
Sure, but I'm just, because we're taking logs, I'm ignoring powers. I don't care. For me, like the degree is like 1 over poly.
1 over lambda squared.
Yeah. Okay, so see here, it's kind of the opposite, because here, this is great. This, not so much, because we have this 1 over epsilon here. So it's kind of the opposite to what we saw in K was independent sampling. So here the degree, here the number of samples is good, but the number of random coins we need to make the sampling is not that good.
But at least it's clearly better than the naive.
Sure.
It's like
But kind of I want to lead.
and M is better.
Sure. Those are it's wonderful. But I kind of want to lead to my next slide and give kind of another thing we like to do in pseudorandomness is that we have kind of two objects. Neither of them is perfect, but every one of them is perfect in one parameter. And we kind of want to try and combine them and to kind of win both worlds. So this is kind of the last thing we'll do today, because we can actually compose samplers. And it's not like I'm giving it again because it's like a typical phenomenon in explicit construction. For example, the zigzag product in graphs is also of this type of phenomena. So say, so how do we compose as samplers? Say we have, I want to sample 0, 1 to the m, okay? I taken gamma out and gamma in. So gamma out samples 0, 1 to the m using capital D samples. And then the inner sampler samples from capital D using, say, little l samples. And before you even try to compile this, let's just see a picture. So the way I use the two samplers is as follows. So here's the outer sampler between this guy and this guy. So I choose x1 here. The first sampler gives me capital D points. And then I use the second sampler to subsample from those D points. Okay, so overall I'm spending n1 plus n2 random bits, and I only have L samples. Okay, so I'm subsampling. Okay, so now you can look at the expression. I mean, but if you understood the picture, it's sufficient. Okay. Good. Right, so hopefully n1 plus n2 is basically n1. And the important thing is little l should be significantly smaller than big D. And now you can try and play around, right? You can try to compose KOS independence and expand the random walks, the two things we saw. It gives something. I'll just say that the state-of-the-art construction is actually a composition construction by Schoen and Zuckerman. It composes the RVW zigzag-based construction sampler with an almost KOS independent sampler and gets nearly optimal parameters. How much time do I have? Like 5 minutes. Okay. Yeah. So Now, the actual last thing we're going to do, sorry about that, is to see how we can use samplers for error reduction of algorithms. So say you have an algorithm, a randomized algorithm. Now we don't want to de-randomize it because we don't know anything about it. But let's say it's randomized and we want it to err like very rarely with probability delta. But what if instead of tiny probability, it actually errs nearly half of the time, say with probability half minus epsilon? So you want to amplify or reduce the error from half minus epsilon to delta. And recall that we like to do things randomness efficiently. So we don't want to do the naive solution of just repeating the algorithms using fresh randomness. So it feels like samplers were really tailored to that, and they really are, because just take a delta epsilon over 2 sampler, draw a left-hand side vertex at random, compute the algorithm, same input of course, but let the sampler tell you which are the randomness strings you need to use, and compute the average. If it's more than half, say the algorithm, say X is in the language, and otherwise say X is not in the language. Now, let's denote B to be the set of randomness strings for a fixed input under which the algorithm says yes. Note that fx is good in terms of it approximates B well. Then this tau minus mu of B, and mu of B is just the expectation of A of W on a uniform randomness string, is close to, is at most epsilon over 2. So if you kind of, spend a minute, you'll see that if W is in the language, then our tau is at least half plus, well, not epsilon, but epsilon over 2, because we have this epsilon over 2 error. And if W is not in the language, then tau is smaller than half minus epsilon over 2. So our algorithm that we accept if and only if tau is greater than half is going to work. Okay, so we can just use an off-the-shelf sampler to reduce the error of a randomized algorithm. Okay, and this, note that it does not assume the structure on B, on the set of random strings, such that our algorithm returns 1. Of course, it's an interesting question to assume structure on that, and of course, that's derandomization. But here, we're not assuming structure. Good. Thank you.
Okay, so maybe we could take questions offline and see what.